In this chapter, we're going to be focusing on the cost of being connected to one another in a variety of different ways, whether it be electronically, physically, planned or unplanned. And we're going to be talking about the math that goes into building connections in an efficient manner. Like usual, let's get into a sample problem, and then we'll talk about some of the terms from the book that are going to help us to understand the math that goes into solving these problems. So I'll go ahead and read the sample problem. 10 communities in Problemtown currently do not have power. Problemtown Gas and Electric has been hired to build power lines so that all of the communities have power. They determined that the theoretical cost in millions of dollars of building these power lines between each of the towns, and the information of each of those costs is provided on the given graph. What is the most efficient way that Problemtown Gas and Electric could actually construct these power lines? So essentially, as we're looking at the graph here, we're left with a lot of information. We can assume that each of the vertices is the towns in Problemtown, and basically each of the lines is representing one of the potential power lines. So as it's currently none of these power lines have been constructed, and the hypothetical cost of actually building them is what is given by each line and the numbers. So we have graph, and this is an application to graph theory where the vertices representative of the locations, or what are sometimes called nodes in a network problem, and the edges or the lines which are weighted corresponding to the cost of construction are sometimes called the links, just as we called them in chapter 6 as well. In these problems as well. So what we could do is imagine, well, what sort of configuration are we looking at, and what math goes into that? And what's actually quite nice is the way to solve this is very similar to how we solve Hamilton circuits from chapter 6. There's just a slight alteration in the process, but there's a lot of similarities to what we've already covered. But let's get into some of the quick terms for a second. And since this chapter is on networks, it's kind of helpful to know what does that mean in the context of the textbook or a mathematical definition. But basically, it's just another name for a graph. So a collection of dots and lines. Typically, they're weighted, as in this case, where we have numbers, also within their graph. Anyways, the terms, when we call the vertices nodes and the edges links, as already mentioned, and we're going to be typically dealing with networks which are simple. Because like in these sorts of problems, we're going to be trying to figure out how to connect the dots together, essentially. And we could think about loops or multiple edges or other complex elements, but those sorts of elements are typically not relevant because usually if we have two towns connected by power lines, usually we only need one connection. We don't need a secondary one, or you usually don't build a power line looping back to itself either, as well. But a network can stand for a lot of different things. It doesn't just have to be a physical connection, but it could be like a series of highways, railroads, anything where we need to get from one point to the other, and we want complete connectedness as well. It could also be representative of, say, internet connections, power, water, things where we're trying to route something from one person's source to another over whatever distance we need. And basically, we refer to all of these as planned networks that we're constructing as humans to serve a societal purpose. We're going to not really be focusing too much on organic networks, but those are also, you can imagine how those can be relevant mathematically as well. But such as a social network, or a network of friends or colleagues or something. Basically, even doesn't necessarily have to be online, but you could think about a friend network, which could consist of each of the dots being people, and the lines representing, okay, if I have a line between these two nodes, that implies that they're part of our network, they're part of our friendship grid, and if they're not connected, then they're not directly our friends. And you can model a lot of social networks using tree or using these diagrams as well. So anyways, the degree of separation is a term that is relevant in certain network situations, which it says is the length of path between the two vertices. Now it doesn't specify is it the longest or what, but the general implication there is it's the shortest path from any 2 points. Like if we're returning to the previous graph, say for example we want to know what's the degree of separation between t and v. In this case it'd be 1, 2, 3. Basically how far apart are they? Or wait, is that actually right? It's actually 1, 2. And this is the thing where you want to be careful because it might not necessarily look like the shortest distance-wise. It's going to be the shortest based on the number of edges. So, and really, if this was say a friendship graph that corresponded to who's my friend, we would say that T and V are not directly friends, but they're friends through one other person. Or that's why it's a degree of separation of 2. They're a friend extended. Or in a family graph or family network, you could imagine that if these were representative of a line was you're my father or son or something like that, then if a degree of separation of 1 means you're a direct lineage, but if you have a further degree of separation, the further and further away you are. Anyways, I think you catch my drift. And in a physical network, the physical degree of separation here for these power grids would just refer to it's further away and give us a sense of the distance between them. Now, a term that's incredibly important for Chapter 5 specifically is a tree. And as you can see from the definition in the book or in the slides, a tree is a network with no circuits called a minimally connected network. So if we're looking back at the power grid hypothetical network construction, this graph would not be a tree because we can clearly see there are circuits everywhere, and it is not minimally connected. But the goal of a network problem is to typically find what we call a spanning tree, an underlying tree which has to do with the graph at hand, which forms a way of connecting all the vertices in a minimum way. Because we could think about this problem as, well, we have all these hypothetical power lines, I could just build them all, right? We could build every single power line in this graph and add up all the numbers. But if we're thinking about efficiency, we don't necessarily need every one of those power lines to actually form a graph. And instead we could focus on building a tree, and that's exactly where we're going to get into. And trees have a few very specific properties, which we'll cover more in detail in the next video.